Hey everyone, this is Venki and it's Lab 4 Circuits and Conductors. So the purpose of this lab was to use a circuit construction kit, or CCK, to create parallel and series RC circuits to learn about circuits' behaviors, make predictions, and take actual measurements. So the format of this lab was basically to make predictions on behavior of circuits, then compare to the actual behaviors on CCK. The first part of this lab was to model a series circuit and determine the change in potential energy. The second part of this lab was to model an RC circuit and use a plot to compute time constant. So for the total potential energy difference across the circuit, I got 0 volts, and then for my time constant RC, I got 5.6338 seconds. The constants involved include the energy conservation, aka the loop rule, and it's also important to understand how circuit elements such as the battery, capacitor, resistor, ammeter, and voltmeter work. For the first lab, I made series circuits, which involved two batteries, ammeters, and resistors. I first predicted the current using I equals V over R, and for this I got 0.0204 amps. And then when I ran the simulation, I found that my predicted value was very close to the actual values, with both ammeters reading 0.02 amps. And even when I flipped one of the ammeters, they still read 0.02 amps. So after I removed the top ammeter and observed the gap using a voltmeter, I found that the voltmeter read 3 volts, and this is because voltmeters read electric potential energy differences, and the red probe had a lower potential energy than the black probe. And then A2, the bottom ammeter, read 0 amps because the circuit was broken after removing A1, so the conventional current couldn't reach A2. So for calculating the total potential energy of the circuit, I found the potential energy at various points, including the battery and the two resistors, and when I added them all up, the total potential energy of the entire circuit was 0 volts, as I predicted. So here's a graph of the potential energy at various points in the circuit, and then A to B, C to D, and E to F are the steepest points, and this is where the battery and two resistors are. And it's important to note that when the voltmeter is attached, ammeter readings don't change because voltmeters have infinite resistance and they don't change the current. And then with the parallel circuit, A2 read 0.06 amps still because the current passed through the wire and through the parallel ammeter instead of passing through the 100 ohm resistor. And then I calculated the resistances of various circuit elements. And then for the 47 ohm resistor, I got 47.95 ohms. For the 100 ohm resistor, I got 102.05 ohms. And then for the wire and ammeter, I got 0 ohms. So this is the second part of the lab. And with the RC circuit with the battery, once the simulation started, the bulb lit up, the bulb charged the capacitor, the current stopped after some time, and the bulb dimmed down. And for the 10 ohm bulb, this all took 11.78 seconds, and for the 20 ohm bulb, this took 21.52 seconds. And you can see that this time is approximately twice as long as this time. And then without the battery, the current went in the opposite direction, the bulb lit up, the capacitor discharged, and then the current stopped after some time. And then for the 10 ohm bulb, this took about 12.19 seconds, and then for the 20 ohm bulb, this took 22.78 seconds. And once again, you can see that this took about twice as long as that. So with 9-volt battery, 0.2 farad capacitor, and a 3 ohm light bulb, I ran the simulation discharging the capacitor, and I measured the voltage using a voltmeter at every second for 20 seconds. And then with this equation converted to its natural log form, I plotted the natural log of the voltage over the initial voltage versus time to find the RC, and then the slope of this equaled the negative 1 over RC. So for my actual value, I saw that the RC was 5.6338, and for my predicted, I got the RC was 30 ohms times 0.2 farads, and I got 6 seconds. So you can see that the actual value is very close to my predicted. So for questions is that if this lab was ever completed in real life, an actual ammeter would have some resistance, so the results for current would be lower. And then if there was a circuit with a battery and no resistor, the ideal model would predict the capacitor to charge instantly. But if this lab was completed in real life, the resistance still exists from internal resistance from the wires and capacitors, so the resistors would not reach full charge instantly. So for my conclusion, we calculated that the total potential difference across the circuit was 0 volts, and this agrees with the loop rule, and that the RC time constant was 5.6338 seconds, and this is very close to 6 seconds. And then overall, this lab did a great job in reinforcing how circuits and their elements function. That's all.